Hello and welcome to Lesson 3. Before we start this lesson, what I'd like to do is to continue our exploration of how polymer processing operations make materials that are used every day worldwide. So, today, let's think forward to winter. Imagine that it's cold outside and that, as ever, energy prices are high, and what heating that you do have in your house you'd like to keep in your house, rather than escaping through walls or through roofs. What's needed is some good thermal insulation. Now, there are many ways in which to make thermal insulation, but one of the products that you see on the market is foamed thermally insulating board. And these boards can be built into wall cavities, into roof cavities, and even into spaces underneath floors. Of course, there are other products such as fibre-based products or fill-based products, but these wall-based products are very useful in many forms of modern construction. And so, if we were to zoom in onto one of these board-based products, what you'd see is effectively a foam structure. And by a foam, I mean that you've got a matrix of a material, usually a polymeric material, and that matrix is interspersed with gas bubbles. These gas bubbles are either disconnected from each other, which we call a closed cell foam, or connected to each other to form this big tortuous void network, which we call an open cell foam. And so what the production process has to achieve is the growth of these gas bubbles within a polymeric base product, and that these gas bubbles have a certain size distribution such they have a certain effect on the thermal conductivity of the material. Now, in years gone by, these materials were typically based on polymers such as polystyrene. Now, we know there are degradation and persistence problems with polymers such as polystyrene, so there are new polymers coming out on the market that hopefully address that, especially when it comes to microplastics pollution. But what we'd like to do is to understand the existing process such that we can then apply that knowledge to improve, to optimize, to innovate new processes. So, these boards are made by a process called extrusion foaming. So let's examine that in a little bit of detail. As the name suggests, extrusion foaming starts with an extruder. It can be a single screw system or it can be a twin screw system, depending on the nature of the specific type of extrusion foaming that's taking place. So in effect, what you have is your base material being loaded into a hopper, as you can see on the whiteboard there, and then that material being conveyed, melted, compressed and pumped by the extrusion system. We then of course need to shape form the product, and so this polymer melt is passed through an extrusion die, and this extrusion die is tailored such that it makes board-like product. So imagine a film casting die, but with a lot thicker aperture at the end. And so the boards that you make might be 1 inch, 2 inches thick, something of that nature. So this molten material exits the extrusion line and then is cooled. Okay, fine. But there's nothing here at the moment that deals with voidage. All we have, if we had this system standing alone, would be a solid product. And a solid product will have a low thermal conductivity, maybe, I don't know, 0.1, 0.12 watts per meter per Kelvin, which is nothing like the insulating properties that are achieved by having a foamed product, because you don't have the gas voids in, which have exceptionally low thermal conductivity. So how do we modify this process to make a foamed product? Well, there's principally 2 ways it can be done. Firstly, you add what is termed a physical blowing agent into the extrusion line at a point where the polymer is molten. Again, in days gone by, this would be a hydrocarbon such as pentane, which has good mutual solubility with the polymer that is molten, for example, polystyrene. And of course, what we can learn from this old embodiment of the process is that you need good mass transfer from this liquid or gas phase into a solution. And so we need to understand properties of solubility, and especially how that solubility varies as a function of temperature and pressure. And then if we understand that, what we can do is to replace these older, more harmful physical blowing agents with newer, less harmful physical blowing agents. There is another way in which you can introduce blowing agents into an extrusion line, and that is by adding something called a chemical blowing agent. A good example of a chemical blowing agent would be something like sodium hydrogen carbonate, which of course under the action of heat will decompose to form little bubbles of carbon dioxide, which then get trapped within the polymeric system. So one way or another, what you have is a means of generating a second phase within the system that will then nucleate and grow to form a voided structure. So let's break that apart a little more. So a point A there in the extrusion line, somewhere beyond the introduction of the physical blowing agent, or somewhere where the chemical blowing agent has started to decompose, what you have is either gas bubbles resulting from the chemical blowing agent, or a solution of your physical blowing agent and your polymer as it's dissolved into it. Okay, this is typically at high pressure and high temperature. Don't forget I said earlier on in previous lessons that extrusion lines can achieve pressures of often hundreds of bar, and that pressure will very rapidly reduce as the extruded product comes out of the die. So the biggest pressure drop in this system is going to be across the die. And so when there's a pressure drop, things that are in solution tend to come out of solution. So what needs to happen for the gas to come out of solution, if we're talking about a physical blowing agent, is that there need to be nucleation sites for bubbles to grow. I think we're probably all familiar with what happens to, say, supersaturated solutions. If you freeze them without nucleation points, you get something like a sub-cooled liquid that, in theory, should be a solid because it's within a solidification temperature, but there's been no nucleation site for those solid crystals to grow on. Same happens here. If there aren't nucleation sites for gas bubbles to grow, they won't, and the gas will stay in solution. And so sometimes what you also add into these processes are nucleating agents, such that you've got a nuclei on which the molecules of blowing agent can attach themselves, form that first cluster of molecules which represents the nucleation site for a bubble, and then that bubble can then grow. And so when the bubble grows, after it has been nucleated, what you have is a mass transfer process going on. You've got physical blowing agent, for example, dissolved in the polymer. Let's say pentane and polystyrene, to take our old school example. And what has to happen is that there has to be diffusion of that pentane through the polystyrene matrix to the bubble interface, and then there has to be a sufficient concentration gradient across that interface to allow the dissolved blowing agent within the polymer to go into the bubble and to grow that bubble. Now, bubbles are interesting things because within a bubble you have what is termed a Laplace pressure, and it is based on the bubble's radius of curvature. So big bubbles tend to have a very low Laplace pressure, and little bubbles have a very high Laplace pressure. And if we think about the relationship between pressure and concentration, we'll see that very small bubbles will have a very high internal pressure, which infers a very high concentration of gas phase. And so the concentration of gas phase within the polymer, dissolved in the polymer, has to be even higher in order for there to be mass transfer from the polymer into the bubble. So the picture I'm painting here is that although the diagram here of the extrusion foaming process is relatively straightforward, especially if we think about it in contrast to, say, melt spinning, where we had our spinnerets and then loads of Godet rollers, some cooling, some reheating, some extra stretching and orientation that was going on. That was a physically quite complex process. This is a chemically quite complex process because you've got heat transfer processes taking place to melt the polymer and to ensure that you've got a good melt. You've got temperature-related rheology taking place. You get viscosity and elasticity changing with temperature, but you've got mass transfer taking place. Crucially, you've got the dissolution of a physical blowing agent within a molten polymer. You might have a chemical blowing agent undergoing a chemical reaction, the first stage of which might result in a dissolved product as well. Then there has to be mass transfer to get that dissolved product out of solution. So you need a nucleation site first of all, and then you've got that mass transfer process from the solution within the polymeric matrix out into that gas phase. So it's a very, very academically and intellectually challenging process to completely understand every single step, because nucleation is actually a very, very complex process, and we're not going to go into those details here. So, extrusion foaming. It's a process that is used a lot to make insulation products, And if you want to actually see an extrusion foaming line working, I've put a link to a video there that you can watch, and I hope you find that interesting.